my beginnings, which was I was very fascinated as an endocrinologist, which is the study of how hormones coordinate energy within the body. The specialty is actually called endocrinology and metabolism. And so as a medical doctor of endocrinology and metabolism, you're looking at the study of the coordination of complex multicellular life to produce energy, metabolism. And metabolism is not done by a human cell, it's done by the mitochondria living inside the human cells. And so endocrinology was this very cool field that most people still don't realize. Even endocrinologists being trained today don't realize that they are being trained into ecosystem science. And it took me 10 years to figure that out. But the exciting thing that really started to happen for me was I started to realize that disease is simply a reduction in that light energy. Disease doesn't happen to a healthy human body. Disease is a symptom of a reducing light potential within that previously healthy human body. And so that started taking my medical career, that this time I'd been in academia for 17 years or something, and I had been basically trained to believe that the human body is super complex and disease is super complex. And so we need really complex biologic chemical science to produce man-made chemicals to modify disease so that you can get somebody back there. And so I had this just ludicrously complex map in my head of like a human body, human biology, mitochondrial metabolism, respiratory and functional enzyme pathways, disease pathways, drug pathways. I almost want to just vomit when I think about how much stuff I had crammed in my head about all this nuanced detail. And then suddenly around 2008 in my science lab, I was starting to really make some breakthroughs around nutrition or nutrients to kill cancer cells. And the place that they were interacting was around this tiny little protein, COOP-TF1, as a regulatory step for the mitochondria to either decide to sustain the life within the human cell or to eliminate life for the human cell. And that process is called apoptosis or programmed cell suicide. And what I was realizing is that I could actually feed cancer cells really high nutrient density and kill them. And it wasn't a poisoning, it was a feed them so much that they realize that they are an unhealed cell and they eliminate themselves. So they literally will just dissolve through that apoptosis. It looks almost like bubble tea, where the cell just like turns into all these tiny, tiny little bubbles and gently disappears. Doesn't require an immune cell, doesn't require inflammation. It just simply releases life. And now, 20 years later, when I'm sitting with all these indigenous wisdom keepers from around the world, you find out that's how we used to do it at the macro level. You would wake up one morning and realize, oh, this is my last day. You would go for a walk in the woods, find your favorite tree, release the body, and you are gone. That's what a cancer cell or a damaged human cell is capable of when it's given enough nutrient. It knows its endpoint and it releases it gently. It says, I can't reproduce anymore. I can no longer repair myself anymore. I have reached the end of my useful contribution to the larger organism that we would call human. And so I'm going to release this human identity as a cell, and I'm going to go back into the ethers, and to replace me as a brand new stem cell that's going to make a new liver cell or a new gut cell or whatever it is. So that's the dance that I've been on over these years, I think, in a long-winded answer to your very first question, which is light is really the definition of a reality, I would say. So what makes a physical reality is light and its many expressions. The difference between physics and biology is a concentration of light energy by at least 1,000-fold to make a single cell and 10,000-fold to make multicellular life possible. And where we find ourselves now is at this diminishing light threshold of humanity, which is leading to this explosion of disease. It's a very fascinating moment, I think, in science where we're starting to realize that life is essentially the distillation or concentration of light energy per cubic centimeter. Physics precedes life. And so physics is basically the periodic chart. You've got lots of elements. Those elements are made of atoms that are crammed together. And those crammed together atoms have a certain number of atomic principles at the nucleus, and then they have a cloud of electrons that are orbiting in kind of a double torus methodology around that. But at the core of that, you either have one proton neutron, which would be a hydrogen, or you've got 16 at a carbon, or, and go ahead and keep building more and more atomic structures at the core of that atomic heart, and you get more and more heavy isotopes or heavy elements on the periodic chart. And the heaviest ones are like plutonium, derived uranium kind of stuff, and all that, those really heavy ones that lead to nuclear power. So the more energy distilled into a single atom, the heavier it is on the periodic chart. And the brightest thing that physics does is that nuclear fission and fusion, and that's what we call a star, or a sun in the case of our galaxy here. And so that star is a nuclear event that's releasing energy from the atomic potential of the periodic chart. And it's fascinating to recognize that to make the leap from star to a single bacteria, you need at least a 10x, if not 1000x increase in light per cubic centimeter. To get bacteria to live or get any form of life to perform, you need an extra concentration of that sunlight. Sunlight itself is not bright enough, does not produce enough energy to sustain life. It has to be concentrated by what we now call biology. So physics becomes biology through the concentration of light energy. So that's kind of a big background of like, what are we talking about with mitochondria? Mitochondria are the most profound biologic innovation in concentrating the amount of light released per cubic centimeter. And what is it? Where is that light coming from? It's ultimately sunshine that's collected by chlorophyll, which are specialized mitochondria inside of plants. And actually, we now know that we have chlorophyll-like activity even in the human body. So when you get exposed to sunshine, you can actually capture that energy as well. But that energy is sunlight stored between two carbons. And so there's a double carbon bond that is formed out of CO2. Two molecules of CO2 become a double carbon. And you start zippering carbons together, and you get a long chain of carbons, and then we call that a carbohydrate or a sugar, or we call it a fatty acid. And there's lots of different carbohydrate structures, and there's lots of different fatty acid structures, but the inherent backbone is this long carbon chain. And to get the fat or the sugar to turn it into energy for biology, you have to break the carbon bond and release the sunshine. And so when I say mitochondria are the biggest innovation in light per cubic centimeter, what's happening is you're collecting lots and lots of potential sunlight in all of the long carbon chains, glucose, sugars, fatty acids, and then you're releasing them in a very small amount of space. And current estimates are that a cubic centimeter of mitochondria, which is roughly equal to a cubic centimeter of human tissue, can release 10,000 times more sunlight than a cubic centimeter the sun produces. And so a human burns 10,000 times brighter than a cubic centimeter of the sun per cubic centimeter. And so that innovation is really what allowed us to leap to this potential of an earthworm or a dinosaur or a human. We needed that much light to produce a body that could self-organize in a womb and produce a living or an alive fetus that would then, without an egg, be born straight into the atmosphere of Earth and be a mammal. And so that innovation of multicellular life all the way marching to the mammals, all the way into, Homo erectus, Homo sapiens, all of that took more and more and more light energy.